So in this course, we've already talked a bit about underfitting and overfitting. What we're going to do in this video is that we're going to illustrate the need for regularization and regression type problems. And we're going to do that with an example of polynomial regression. So consider some polynomial, for instance, the following here. So we have that f of x is equal to 2 plus 8 times x to the power 4. Now suppose that y is actually given by this relation plus some additional noise. So this is the data generating process. How do we learn this true functional form? So we'll try different models with polynomials of increasing order. That's what we're going to do in this example. So what we'll do is that we'll simulate some data based on this data generating process, and then we'll split data into a training data set and a test data set. And just for purposes of illustration, these will have the same size. Now for polynomials of order 0 and up to 15, we do the following. In iteration n, we consider a model on the form y equals to the following sum here, and then plus some additional noise. So this is basically a Taylor type expansion that we're making. So when n is equal to 0, we're basically just fitting a beta naught, just a beta 0, a constant term. But then we do the same thing for n's of values between 1 and 15. So when n, for instance, is 15, we're estimating coefficients associated with a long sum. So we're estimating both beta 0 and then beta 1 that's associated with just x, and then beta 2 that's associated with x to the power of 2, etc. Okay. And what we're then going to do is that we will estimate a model of order n on our training data. So we're going to estimate these the coefficients that are associated with each of these 16 models on the training data. And then we will evaluate the performance on the models on both our test data, but also our on our training data. And we'll evaluate the models using the mean square error measure. Okay, so what we'll do first is that we will generate samples from using the true model. So in order to do that, we first import polynomial features from the pre-processing module. Polynomial features allows us to make this polynomial expansion of variable. Then we also load linear regression from the linear model in module in scikit-learn. Okay. These will be quite handy, and I'll show you that later. But what we do now first is that we define the true function. So that's 2 plus 8 times x to the power 4. That's what we had before. Then we specify that we want 25 observations from both our test data and our training data set, and then we specify a seed number. Okay, and then now we draw 25 x's from a standard normal distribution and make that our training data set, and then we specify, and then we draw 25 new x's from a standard normal distribution and call that our test data set. And then we use these x's to also get values for our y's, our outcome, our target. So we use a true function for that. So we draw one instance of y as one instance of x using this functional form here, and then we just add some noise. And that's how we draw 25 observations of y's from our training data set and our test data set. So we use this true functional form, and then we just add a random noise to each of these observations. Okay, so what we do now is that we estimate the polynomials and store the mean square error for both the training and the test data set. In order to compute the mean square errors, we import mean square error from the metrics module in scikit-learn. And in order to store these mean square error measures and the parameters that we obtain in the different models, we create 3 empty lists here to begin with. Then we specify that we want to estimate polynomial models of up to degree 15, and then we create this range here of values going from 0 to 16, excluding 16, right? And then for each of these values in this range, we do the following. So we create X train P as a polynomial transformation of the original training data set. So instead of just having 25 instances of X's drawn from a standard normal distribution in X train, we now make this polynomial transformation with polynomial features of up to degree P. And then by specifying a fit transform on X train and on X test, we are making these transformations on both X train and X test and store these as X train P and X test P. Okay. What we now do is that we use the training data set, this transformed training data set, to fit a regression model. So we specify a reg, that's our fitted model, and we use the linear regression here drawn from the linear model module in scikit-learn, and then we fit this type of model on our transformed training data set, and using both the features and our target. Okay, so here we're basically estimating the coefficients associated with a polynomial of a given order on our training data. And then we use this model to obtain the mean square error on both of that measures the performance of our estimated model on both the training data set and then also on the test data set. And we keep these measures in the lists that we created up here. And then we also store the parameters in this list of parameters up here. Okay, so we evaluate the performance of the model that we have trained on the training data set, first here on the training data set and then on the test data set. And then we also store the models that we obtained with this fit. Okay, so now we may ask, what happens to the model performance in and out of samples? Okay, so that's what we plot here. So the blue line plots the performance of our model on the test data for polynomials of different degree. So we want as low a mean square error as possible, right? Because that means that we have predicted that we managed to predict the y's well if we get a low error on our predictions, right? And then when we consider the red line here, these are our measures of the mean square error when we evaluate the performance of our model on the training data set. So if we first consider the red line here, we can see that for a more flexible model, when we fit a model that has a higher polynomial order, the performance simply just becomes better, right? And that's because we have a more flexible model can basically just represent more of the patterns that we observe in the training data set. But that's not the case when we consider the blue line here. So we can see, as to begin with, the performance on the test data is basically the same as in the training data. So that's when we basically just it's basically just equivalent to fitting a mean here. But then the performance of the model increases when we allow for a higher polynomial order that can actually capture the true relationship in the true functional form here. But now, when we have trained a model that is too flexible, we see that the performance of on the test data drastically becomes worse, and that's because when we estimated a very flexible model, we implicitly allowed our algorithm to learn too many spurious relationships in the training data set, relationships that do not have anything to do with the true functional form. So that's why the performance on training data set, it keeps becoming better, because we can just make a more flexible fit of what was present in the training data set. But when we look at the test data set, we can just see that we doing so, we just fitted too many spurious relationships in training data, relationships that do not hold in the test data. Okay. And I don't want to spend too much time on this quiz because I gave you the answer already. But what we got was that with a higher degree of the polynomial order, we simply just estimated too many spurious parameters, and these weights, they just fit some idiosyncratic noise that's unrelated to the true model. What we also see is that the coefficient sizes, they increase at a higher polynomial order. So that's what we show here. This is the mean parameter size in different models. So this is the phenomenon of exploding coefficients that we will see when we basically are overfitting our model. We can see that the mean size of our coefficients, if we disregard these first values, it's minimized around the polynomial order that's actually associated with the true model, right? 4-5 in the 4-5 range. And then when we fit a too flexible polynomial, the parameters clearly explode. So what you should notice here is that we have a log scale, right? So these are very high values for the parameters. Okay, and just quickly to visualize the ideas in this problem, we've already seen this before. So this is basically what's going on here. So the green line here represents the data generating process, and the red line here represents an estimated model. And this is just another hypothetical example here. So what we had here first was a nice convex relationship in the data between x and y. But what we can see here is that when we fix a very simple model, it's not really capable of capturing the true data generating process, because the true data generating process is just not that simple. So it cannot be captured by this simple model. And that's basically going back. That's basically what we saw with these high mean square errors here, right? We simply just had a too simple model. We could not capture the true the true functional form in the data, the true data generating process, and that's why the performance on both the training data set and the test data set didn't become very well. Then here we have a balanced model. So that's when we estimated a model that allowed for polynomials up to degree 4 or 5 in the 4-5 range. Then we have an appropriately flexible model that can capture the true relationship in the data. But then when we have a too flexible model, we can see that we're just capturing some spurious relationships in data. We're capturing relationships that have nothing to do with the true data generating process. We're just fitting basically noise, right? So that was, again, going back, that was what happened here. Then we could see that our performance on the training data set, it just kept improving for higher order polynomials, but that was just not the case in our test data set, because we just fitted noise, basically.